want to go and try the page cache lab on a MR /11 SP2 MR kernel. I should probably have gone back to a PTF kernel, but I chose to just pick the official released /11 SP2 kernel that came with the media. Actually, let me get out of this window. I can see I just rebooted it, and I do have the original kernel. Let me bring up a better window here. I don't want to use a console window for work. I need that for if trouble starts. Uname -A. So I've got a 301327 kernel built in February. I'd like to try I didn't like something. The one that I've been using is a 304273 kernel, which is what you get from the Novell Update server right now. But I did have a special patch applied to it for a memory C group hang that I had a week ago. But it's basically 3042. Get out of here. I'm going to do sysctl-a and grep for dirty and topology. Oops. And I should get my PM chart running here, particularly in this area. I mean, I was explaining earlier in the week, I don't care what tool you use to get to the data. It's the interpretation of the data that matters. But when it comes to ProcMem info and looking at my memory, it's kind of easier to visualize that memory stack bar, memory footprint that I've been building. So I'm going to bring up my PCP. Oops. What did I get? That's not what I wanted. Well, let me see what I've got for review here. I'm just going to go up and let me click here. So I sent you a copy of that view yesterday. However, you're still going to have to make changes to it, but it's a basic starting point. See what mine gives me. Oops, I got to connect to the right host. That requires the PMCD daemon to be up and running in order to connect to it. But in your case, I think you've got an older kernel that does not have things like compaction, things of that sort. Different file system design here too. Different NumoLink, different nodes. Let's see what we got here. I want to start off with overview. So I'm looking at CPU, memory, swap I should say, then memory, then disk, load average, and file system full. Let me get a larger interval. I'd like to see more data. You can increase it past that, but you have to start up PM chart with additional options. Memory in particular is what we're looking for. So we've got page tables, slab. It does look like I have a 50 gig slab on this system right now. Oh, wait a second though, hang on. Remind me, I was looking at Floyd 1, not Floyd 3. I went to the wrong system. I've been doing all my labs on Floyd 3, but in this case I kept Floyd 3 at the original update kernel. And also keep in mind, in a large CPU system, no, the NumaLink ports are different on this one. That would be expected. Let me close that chart and reopen it. This is what you're going to have to do as well. You're going to have a whole different NumaLink port list of UV and L traffic, and we're still going to have to start it with the linkstat UV command. I like to look at send bytes. Apply that. For the fun of it, I never really actually do this. Let's look at the commands, protocol, not just data transfers. Sends. Your port layout is going to be entirely different on your system, and you're going to probably have a pretty big one.
Mm-hmm.
I don't like to stack bar them because particularly with a lot of ports, it's hard to see anything. Again, to get the statistics working, link stat dash UV dash capital A. Keep in mind when you start getting a lot of dirty data and lots of writes and stuff shuffling around between the nodes in a spread pattern, your interconnect is going to go up. And if your interconnect gets congested, that's going to create impact on the system. I'm sure we felt that a couple of times, and we're able to see where the NumaLink traffic just peaked, and then we actually dropped data for a while. The NumaLink and the QuickPath can become saturated. In fact, I should show you this now in Dev CPU set. We've got these spreads. We get into that next. This is what's spreading everything across all the nodes in the CPU set, but I only have one CPU set here, the global CPU set. So that can tie up and make congestion on the interconnect. So that's why I want to see the interconnect traffic with this experiment. So there's my CPU, my swap, my memory. Again, this is real small. That's pretty unusable. I/O operations, reads and writes. Total, same thing as SAR-B. Load averages, file system full I don't really care about. Here was the key one before I realized I was on the wrong system. Page tables, dirty. By the way, let me check something here. If I click in here and edit chart, it shows here that the metrics are from Floyd 1. So page tables, the slab, again, the system just rebooted, so it's pretty empty. No dirty, right back, no NFS, it's all clean. Take a look at paging, no paging activity right now. Again, the one that I sent you, your kernel probably does not have compaction or UTOP. Some of those things were taken off. I'm going to get rid of unevictable as well. NumaLink traffic. The other one I want to do here that I sent in your display, let's add a tab, node info. This will also have to be reconstructed on your system, but you've got to do
Yeah, I started looking at that last night, but
yeah,
I didn't have a clue what our nodes were because I haven't really worked on our UV at all.
So a node is a socket. Every processor socket has memory attached to it. That is considered a node. And everything about these systems is to lock yourself down to a node and stay on node or on socket with everything. Does that help?
They're numbered, right? Like node 1, node 2, node 3?
No, they start at 0, node 0 on up.
Node 0 and up, okay. So I just need to find out how many nodes we have then.
Yeah, it'd be the number of sockets, tuber blade, number of blades. So under MEM NUMA utilization, this is where I had them per socket. I can't put everything on here, so I want to primarily watch for free because I want to keep things free. So I've got 2 blades or 4 sockets. Okay. Let me apply that one. And then the other one I was going to do was used. And we're going to come back to NUMA awareness in the CPU set module after a break. So I had free. I wanted to get used. And apply that. Now let me review that for you. Oops. So with the topology command, we can see that we've got 2 blades. Now what they call a node is different. These they're calling a hub. Those are nodes in the interconnect, not Linux nodes. By doing ls on /sys/devices system node, I can see how many nodes I have. And each of those has a MEM info.
Whoops,
So that's the sockets you have. Now, I did have one site where they had a CPU and a socket applied, but they had stripped all the memory. They harvested memory chips incorrectly off the blade and left a socket with no memory. But in generally, every socket has its own privately attached memory attached to the socket with a memory bus interface.
Yeah. It looks like we've got, I just went in there and it looks like there's over 200 nodes. Does that make sense for our system?
Sure.
255 it looks like.
Are typically 256 nodes. Type in topology and see how many blades you've got. I
did that topology and I got a gazillion. It was a huge printout.
Just pipe it into more or something, the header of it. The newer version of topology just has a short version. We've changed the syntax on it.
Oh, okay.
So that it's less verbose. But try piping it into more.
Okay, I just did that. Okay, here it comes up. Okay, so 128 blades, 48 routers, 2048 CPUs.
Biggest system that we can put is almost 2048 CPUs versus 4096. So these are probably not hyper-threaded. By the way, type in CPU map.
CPU map, okay. Okay, I've got a listing that goes from 0 to, there's more stuff on top of that, I think.
Yeah, pipe it into more.
I think I'm going to have to, yeah. Okay, I've got that. Oh, and it's got the hub locations. It looks like NumaLink numbers, eh? Except there's an awful lot of them unless they're repeated.
I would assume hyper-threading is off on your system?
Well, I can't be 100% sure because I don't normally work on it, but I do know that in general we don't like hyper-threading. Oh, here it is. It says it's off.
Yeah, that's what I was expecting.
Yeah.
So then you get physical CPUs, and again, my report here is showing 4 cores per socket. How about yours? You're probably Westmere with 8, or?
Okay, here just for, okay, yeah. Total number of cores, 2048, 8 per socket.
Uh-huh. Okay. That all sounds like Westmere. And when you're in a CPU set situation, then that CPU map is also useful to show you what processors. In my case, I have hyperthreads on, so there are parentheses around the hyperthreaded logical CPUs. Hyperthread basically says there's 2 states on chip, 2 program counters, 2 sets of internal registers. When you context switch, you can flip between these 2 states, but they still share the instruction pipe, the caches, the functional units. Okay, so every one of those sockets has its own node, its own memory. So there is a node info for you as well, but it's basically too big of a system for node info to really help you. And this is going to show you every socket, every node, the data that I'm plotting over on the left. So I'm basically looking at the free column and the used column. And here the free column is in the 31, 32 looks like, and then the used column is 500 to 800 range, which is what I see over here. So all this data that we're looking at right now on a per node basis is coming out of /sys devices system node, and then the node number, meminfo. Those are the 4 meminfo files that I'm plotting over on the left. Okay? So, moving on with my page cache experiment, I wanted to see about dirty data thresholds. sysctl-a, let's prep for dirty. Oh, let's add these sysctl.conf. Looks like they've already been changed during the boot process. Now they are hard-coded so that they should not go more than 50% dirty, even though I've got them higher than 50% dirty. But I'm also going to start flushing after 30 seconds. Let's just see what happens here. So I can see some dirty data going on here. Let me get rid of free. There's the dirty data going on. The question also is, we do have disk activity happening right away here. Now, how dirty can it get? So I can see some flushing activity going on down here. Go back to memory. Let me take the, so there was a flush that started right there at about 2.5 gig. I was not expecting that because dirty background ratio was set real high. Let's, what about the write backs? Get rid of this stuff. There we can see the write backs right in there. And it looks like I'm only getting, well, let's see here. Add the dirty back in. 2.5, 3 gig of dirty data before I start flushing. And I don't think I hit dirty expire centiseconds. Now let me do a kill all on these things. I'm seeing something interesting here again. The flushing has stopped at this point. I still got dirty data there. I'm not seeing any sort of flush happening. I want to wait for like 30 seconds. Let's double check that. Oh, there we saw the flush. Trying to figure out what the time interval is, but again, you can almost see the periodic wake up. Let's take a look at the right backs alone. And that's the waking up of the flush demon to do the flushing. Oh, let me try something else here. So I'm trying to slow down the flushing so that I can see the effect of one of the parameters. And I'm trying to have a higher intensity IO, having more than one IO thread at a time, pushing on the bottleneck. Let's see what happens this time. There are the DDs running. Notice they have an R. They're in a running state. We just had a metadata journal log flush occur. I see the dirty data going. Question is, how much dirty data will I be able to get? I just had a DD go to sleep on me. And we can see the IO and the disk activity did start up right away. Get out of here and get 3 out of there. I want to let this go. So we do see processes going to sleep right now, even though we're in the 3 gig range of dirty data. So I'm not seeing the effect of those thresholds right now. I'm looking up here. The process has been killed, but I still got 5 gig of dirty data sitting there. I want to see if the flush demon wakes up here. This is how often the flush demon will wake up, every 5 seconds. But I've extended this now out to 300 seconds, not instead of 30 seconds, I added a 0 to it because those are in centiseconds. So I got some dirty data sitting there. Let's see if I'm flushing it. no disk activity. So once I killed the process, the data that it wrote is just sitting in memory and is not flushing. Let's see how long it takes for it to flush. A sync command will start a flush. I'm just wondering if I'm going to get a flush due to dirty expire centiseconds. Kind of waiting for, take dirty out, waiting for a flush here. So we've got for time axes down here. Every one of these ticks is about 30 seconds. So a sync command will force that flush to happen, but I don't want to do it that way. I'm trying to test the flush demons. I've got 5 gig of dirty data sitting here. Let me do a change the time. Instead of 3,000, or 30,000, let's try 3,000. That should say anything over 30 seconds should get a flush. We got to wait 5 seconds for the flush demon. There we are. We just had a flush. Try that again. I'm trying to get the flush by age out of the picture and see the effect of the background ratio and the dirty ratio. Let's try upping those a little bit. Actually, I probably should I'm trying to fire off the dirty. Again, there's some flushing going on right away right now. Trying to grow a little bit. Let's take a look at the, there's a little bit of disk activity there, but then it stopped. We can see some system time associated with that write. Then there's a little bit of I/O wait time after it where the process goes to sleep. Then some system time. These sleep-ons are part of what, I do have to be careful about the journal, but these, everything's running right now. All system time, by the way. Now we're going into a sleep state, so we're correlating the two actually. Let's see here. So we're in system time. Now we're in a sleep state. I'm not seeing the flush demon show up here in actuality. I can see the flushes periodically happening here. Let's do a perf top. The system time I can see is related to that mutex spin on owner. I also see the journaling activity involved in here. Every time a file is growing, we have to be able to, even my PCP, by the way, is stalling out on me. Not real heavy on the bandwidth here. I'm 500 megabytes. I'm not seeing a whole lot of pressure there. dropping data. It's still only in the 2 or 3 gig that's dirty. Got kind of poor response right now. Actually, I had the console already, but let me just grab it again. Oh, we dropped the KDB. Not good. Try to go. I did come back. Something dropped me to KDB. My system time is back. Let me try a perf record -A-G. Did I drop the KDB again? Yes, I did. That's one of the reasons not to use this kernel, by the way. It's sensitive to the perf utility. Let me see if I can break out of that. Probably should have gone with a PTF kernel too. Kill that process perf and see if I can get the system back and running reliably. Okay. We were trying to look at that system time, but the perf utility was causing a drop to KDB. There's a known patch for that. Let's see what's going on with our I/O now. We know it was a mutex lock, and we were able to see it yesterday on the newer kernel. Perf was more reliable. There's my dirty data going. I just want to see how dirty I can get the data. Also, I was going to try something else here. So let's take a look at the system now. SAR showing me all that system time. Perf top was showing us that it was a mutex lock that's involved in the I/O. SAR-R 1-5. Only 11% of my memory is used. I do have a 14 gig cache. Let's do a SAR-DP. This is what we've been seeing, the disk activity. You can see SDA where these files are being written to. The drive is like 100% busy, and I'm getting a half a second waiting for a disk request on average. Let's cat/proc/mem info. No NFS data, My slab is still small at half a gig. No shemem. I did have dirty. I'm seeing here 10 gig of dirty data at this particular point. Slab top. Buffer head being the biggest thing in the slab, and that's what's describing my dirty data. Half a gig there just for the buffer underscore head. How big is it now? It's up to 12 gig. I can see occasional wake-ups of the flush daemon. There's something else I was going to do here. Before I do that, I bring up top disk. Oops, there's top. There's my SDA, writing in 400 kbyte chunks. We can see where it's going to sleep, but there's a periodic thing going on here with the flush daemon periodically waking up. We can see the dirty growing in memory here. Our system time is now all system time constant. Do a top sys. The journal daemon is going to be one of the things here. A journal D, but mostly it's all these DDs. And I don't really want to attach with perf right now because I was dropping to KDB. But all that system time is from write IO right now. Memory, again, I'm up to about 15 gig in dirty. And I should be able to get 30%. I've got a 128 gig machine. I don't know, somewhere around 50 gig. Let's bring up a calculator, get a better idea. (42, 43 gig was where flushing was supposed to start. And we should be able to get up to 40 gig or 40. Let's try that one. 128 gig. 40% of it. About 32 gig. What was it? 51 gig before I stop flushing. I can't have any more dirty data than 50 gig, it looks like. Let me see if I can push this up a little bit more. df-h, first of all. Oh, I'm 100% full on my disk drive now. Let's see, by the way, what's going on with write-backs now? Okay. Periodic flush, but you don't see anything really. So I'm at 96%. I was going to go into var temp 2. I'm looking for files I can get rid of. What's that disk space is not going to be recoverable until I actually see the file, the process and the flushing of the dirty data flush from memory. Got some reads going on now. Looks like there's like a flush right there. Can't see it there. The Numalink isn't too bad tied up here at 400 meg. We've got on a per node basis. Lots of memory free on a per node. We're down to about 25 gig. Notice that all nodes are being allocated round robin. They're all tightly aligned in their memory growth for this dirty data. And also keep in mind, well, let's see what's going on here now. I'm surprised cached here is so small. Oh, I did have a flush there. Once the file was removed, everything in the cache was gone. Okay. Do I have my disk space back? I do have my disk space back. Notice removing that file is reading in metadata. We got some sort of read activity going on there. Got 48 gig in one and 65 gig in another. I'm trying to increase the intensity of the I/O. See how quickly it can grow the dirty. But I can see the writes were starting right away. We do a kill all. So I killed the processes. The dirty stopped growing. I do have some disk activity still flushing it. Go back to memory. Let's just add in cache clean here. You can't see. There's no flushing. I don't see it going to cache clean at all. System time has stopped. The flushing has stopped. So now let's try dropping the sysctl parameter down and see if that's going to kick in the flush. I still got to wait for the flush daemon to wake up, but that was a 5-second interval right here. And I'm not seeing it wake up. We try dropping dirty ratio down to 5. No flush. Get rid of, oh, we just had a flush start. The dirty ratio did kick it in. There's my flush. At least I think that was it. Try that again now. Drop the dirty ratio up to 50. But you can see flushing did start anyway, even though we're, the dirty background ratio is still at 5. So we should see flushing start right away. The question is, how much will we be able to get dirty? So I have another way to test on this. Right to a slower file system. There I can see now, writing to the slower file system, I am backing up in my write backs. Let me add in the NFS unstable. Oh, it was. And we can actually see it going from dirty to write back to NFS unstable. Now the question is, how much of this can we get dirty? So I do have dirty ratio at 50, so we should be able to get half our memory backed up dirty, particularly since we're writing to a slow NFS file system. Let's see what this does. We should see a flush come here and everything go to write back. Not everything, because some of it's going to temp, but put in cache clean as well, so you can see this is all the writes that we're doing. It's going from dirty to write back to NFS unstable, and then as it's flushing, it's going to clean. There, we just had a flush. Big one. Since the write backs went small too, I'm almost believing that that was a flush to disk. You can catch the disk I/O for that. So there you can see that big flush we just had. That happened at 10 gig. Let me up the ratio of dirty background ratio again. Again, I had taken this real long to be able to get the flushing by age out of the picture. And I'm just trying to see the effect of dirty ratio and dirty background ratio, the point at which I start flushing the disk and the maximum amount of memory that it can have in a dirty write back NFS unstable situation. It appears that I'm flushing before I can actually get to the dirty ratio. Let me take cache clean out of the picture. Another thing I want to try here, LSOF. So this is allowing me to catch all the data that's in the page cache, as long as the file is open. Now, if I were to go onto a different system, let's go to Floyd 2 here. You got to be able to throw away junk. This is what we saw the other day with share text in here, started by this field. So this is a quiet system. Also, people usually only look at regular files instead of getting things that are not regular, open sockets, things of that sort. So let's kind of take a look here. Lots of system time. I don't want to pull apart the system time because perf is going to drop me to KDB. Got to be real careful with perf. What am I getting here? So we see a rise. There's another flush there. I can see constant writes going to disk. *R 1 space 5. 27% of my memory being used. *DP 1 space 5. With the large disk farm, I usually just let it go to the end and then look at the averages for the interval. There I can see root is 99% busy. I've got a 1.5 second wait and an I/O request there. And bandwidth there. Let me do a VI and /temp/my file. Let's see how long it. Oh, I got that back pretty quick. Trying to write it. Came back. Oh, I'm still waiting for my write to finish. There we are. You know, top disk. Everything's on root, so it's going to be hard. SDA. I see SDA 3 and 4 busy. So SDA 3 at DF. SDA 3 is / and SDA 4 was data 1. Let's use an fuser -UVM on /data 1. Oh, it's having trouble getting to home. What did we have for NFS unstable? Here, let's get rid of the dirty. You can actually see again the wake up of the flush demons and a flush. Here's where a whole bunch of NFS got flushed and got marked as clean. Keep in mind, buffer _ head is describing this whole thing here. As it gets bigger, the slab's going to have to grow too. Let's put the slab in here. You can see the growth of the slab from this. Put dirty back in. Can't even get anything out of that right now. I'm going to try to log in as guest. Taking a little bit to log in, it seems. Still can't get logged in. Let me log in as root. You're going to get logged in as root because root does not have /home in his path. Home is not full yet. It's just having response problems. Got 60 gig. Half of our memory is cache clean now. I'm actually a little surprised it's keeping up as well as it is. The other day we had quite a bit of NFS backed up traffic, but I think we had multiple threads at that time writing to the NFS server. Oh, I did get logged in as guest. Let me try IO top. DD, the metadata kjournal D for what's going on, and lots of other DDs. Now, sometimes I'm going to warn you, sometimes you're going to see numbers here that are meaningless in the terabyte range. That's just a numerical discrepancy. Don't worry about it. I can't take these numbers too serious. They're basically what's in the proc PID IO file divided by the rate interval of the sample you're looking at. And that elevator is not the physical IO layer. The elevator can suck up IOPS, and it looks like you're getting lots of work done, but then the back end of the elevator is not actually initiating the IOPS to the device. There was something else I was going to do here. Got off tracked on it. Block IO mon. Having trouble even getting a man page going here. I'm still only dealing with about 10 gig. I can see a lot of NFS write back marked there. I'm still only talking about 10 gig or less, and it's giving me problems here. We'll see how this works in a CPU set situation later. Still lots of disk space. There, I finally got my block IOM on. I want to try this here. Oops, need to specify the path I want to look at. Now, top disk and SAR-D are coming out of the proc disk stats file, which is at the elevator layer. This is actually looking at the individual I/O operations, looking at the elevator packets themselves, not some sort of average. This is a histogram in terms of size and times on an I/O request. I'm seeing most of my I/O requests are in the 512 kbyte range. And I can do a, notice directory's empty. Let me do a block trace /dev/SDA. And it's going to fire up a probe for every CPU. Let's see if we can catch it here with top. There's going to be a trace file for every CPU and what they can see for I/O operations on that particular CPU. Not seeing anything there, but let's do a ps-el. Taking a long time for that, too. There we are. Here's the block trace command that I was running. don't know what happened to my zipper. Let's break out of here. So now I can see on a per CPU basis the events that were looked at there. There is a file for every CPU, but now you need to run a bparse or some sort of command to filter that trace file. Those are binary files. They're all data files. So there are different tools that can process those generated traces. Here they did a block parse -I, for example. Let's just try that on one of the files here. Let's do a block parse. This one right here looks good. So here we're actually looking at each individual IOP. I'm not going to break all the fields apart here, but we got major, minor numbers, the time sequence, the type of packet it is. Here I can see DD writing. This is the position in the device, and then this is the size of the I/O request. You can see processes being initiated or dispatched, actually going active, dispatch meaning they're put on the queue, going active, and then a complete. There are a variety there. I can see all my metadata, my kjournal D data too. But there are a variety of ways of looking at this data. There is a plotting tool called SeqWatcher that can go in and plot this stuff to see where our head movement is. Okay, ES-E. Let's do an S trace on one of those things, -S-P, on 8111. And I picked one that was really, looks like it's maroon. It's not, that might be the NFS one. Let me just break out of there. I can. Pick a different one. There we can see the I/O request read and write system calls in 512-byte blocks. That's going to be very inefficient since everything else is in 64 or 512 K-byte chunks. So the cache is coalescing these things together and making them into the $450K, $500K range. 461. Again, this was an average, and then BlockTrace looked at each individual IOP. What am I doing back here? About 20 gig of dirty data. I thought I'd be able to get up to 50. Let me see if that makes any change. It looks like I killed that one thing. Let me do a kill all DD. looks like killing them stopped the flushing again. There's where the kill was. We do still have some disk activity going, it looks like. But I have to remember that I also killed what was going off to the NFS server too. No more data being written, so we can see that cache clean has topped off. And here was a flush, here was a flush. Can we catch any of that in disk? Not really, because we've got a constant write thing going on. We do have some IO8 going on right now too, which is probably the flush daemon itself. Oh, and the journal daemon, the metadata. There's the flush daemon. But that IO8 is finished now. The disk activity has stopped. But I do still have a little bit of dirty data in there. We still got 6 gig of dirty data. I think we should take a break here. I've got 20 minutes after the hour. Let's come back in 15 minutes.
Yeah. I might be a little bit late because I've got an issue I got to deal with while staff are still working here because nobody's going to be here on Monday.
Sure. How about we come back at 1:45 and see what happens? I want to see this dirty data, whether it ever flushes without me doing anything.
Okay.
We come back at 1:45.
I'll do my best to be back by 1:45.
Okay, so we'll see you at 1:45.
Okay, rightio. Thanks.
Sorry? Hello? Hello?
Yes?
So you said we will come back at when?
1:45.
Oh, okay. Okay, thank you.
About 25 minutes.
Okay.